Every single second, just billions upon billions of messages are zipping around the world. I mean, think about it. High-def videos play instantly, encrypted emails drop into your inbox in moments, and we're having live video calls across entirely different continents with, like, zero lag. We're so used to it that it feels kind of magical, right? Like data just materializes out of thin air. But actually, behind every click, every single search, and every stream is literally one of the greatest physical engineering achievements humanity has ever built. So welcome to today's Explainer, where we're going to embark on this epic journey to break down exactly how data packets travel globally. We're going to trace the precise, highly physical path of your data from the exact moment you hit enter, all the way across the globe, to the instant a website renders on your screen. Let's dive in.
To really wrap our heads around this journey, we first got to ground ourselves in physical reality. We need to ask, where does the internet actually live? Now, the tech industry absolutely loves to throw around the term the cloud. And sure, it's a super convenient abstraction. It makes our tech sound, clean, wireless, and kind of weightless. But actually, let's just strip away that abstraction for a minute. The internet is heavy. It is a sprawling, highly physical network. We're talking about billions of connected machines, homes, offices, cell towers, and these colossal data warehouses. And they are all physically tethered together across the planet by millions of miles of actual physical copper and glass.
And at its core, this mind-bogglingly vast network operates on one remarkably basic foundational rule. Send information, receive information. That's literally it. Whether it's the smartwatch on your wrist or some multi-million-dollar supercomputer, every single device connected to this giant web shares that exact same goal. The true marvel of the internet doesn't actually come from some incredibly complex underlying directive. It comes from how ridiculously fast and efficiently billions of machines execute that simple binary rule, all at a truly planetary scale.
Okay, let's anchor this massive concept to something we do every single day. You open your browser, you type in a website, let's just say youtube.com, and you press enter. To us, the response seems practically instant, but let's slow down time for a second, to almost a standstill. In the literal fraction of a second between you pressing that key and seeing the page load, you are kicking off a vast, highly coordinated global expedition.
The very first step of this high-speed expedition, it's all about translation. Because fundamentally, computers do not understand human language. The hardware doesn't have a clue what a youtube.com is. It only speaks in numbers. And this is exactly where DNS, or the domain name system, steps in. Think of DNS as the internet's ultra-fast phone book. You ask it, hey, where is YouTube? And it translates that human-readable name into a machine-readable numerical address. This system handles hundreds of billions of queries every single day, and it usually knocks out your request in just mere milliseconds.
So, your computer takes that familiar human-readable URL, www.youtube.com, and queries the system to find its actual digital IP address. It's going to look something like 142.250, and so on. Honestly, just think of that IP address like a specific street address for a house. Without this crucial mathematical translation step, your computer would have absolutely no idea where on earth to send your request. But now it has the exact coordinates of its destination.
Once that destination is locked in, your computer doesn't just, chuck one massive, clunky file across the world. Instead, it uses this brilliant concept called packet switching. This is what makes modern networks vastly superior to old-school telephone networks. First, it breaks your info down into tiny, manageable little pieces called data packets. It's kind of like trying to mail an entire house. Instead of sending one impossibly huge box, you're mailing thousands of small, standardized envelopes. Next, it slaps some vital metadata onto each envelope: the sender's IP, the destination IP, and a very specific sequence number. This is crucial because it ensures that even if these packets take completely different routes, they can be perfectly snapped back together later.
All right, so these newly minted packets leave your computer, and their very first stop is usually just your local home router. Your router is essentially the initial director of this whole global journey. It acts as your local traffic controller. Its entire job is to look at those destination IP addresses on your packets, consult its complex routing algorithms in a literal fraction of a millisecond, figure out the best initial path out of your house, and just push those packets forward onto the wider grid.
Now hold on, because there is a massive misconception about how this data actually crosses the globe. With all the hype around modern tech, you'd probably assume your data is beaming up to space and bouncing off some shiny satellites, right? Well, the reality is strikingly terrestrial. Satellites actually carry only a tiny fraction, around 5% of global internet traffic. A staggering 95% of international internet traffic travels through physical cables lying deep at the bottom of the ocean. Crazy, right?
This network forms this incredible, sprawling underwater light highway. We're talking about cables stretching for thousands of kilometers, connecting continents across the vast, dark, abyssal plains of the seafloor. And here's the wild part. The actual data-carrying core of these cables, it's often no thicker than a garden hose. Yet, they are wrapped up in multiple heavy layers of copper, steel wire, and polyurethane just to survive the immense water pressure, tectonic shifts, and yeah, even the occasional shark bite. These highly shielded physical cables are literally the backbone of the modern global economy.
But what's truly mind-blowing is the physics happening inside those protective layers. Your data isn't traveling as some standard electrical current underwater. No, it actually transforms into rapid pulses of light. Inside these ultra-transparent glass fibers, lasers are flashing billions of times every single second. Each microscopic flash represents a digital 0 or 1. Thanks to total internal reflection bouncing that light perfectly along the glass, your search request is quite literally moving near the speed of light across the bottom of the ocean.
So, after crossing oceans and continents in mere milliseconds, your light-speed packets finally arrive at their destination, the data center. This is where websites actually live. If you were to walk into one of these facilities, you'd instantly be hit with the deafening roar of industrial cooling fans. These places are massive, highly secured warehouses filled with acres upon acres of server racks and blinking LEDs, and they consume enough electricity to power small cities. When you request a website, it's being pulled directly from these intense industrial-scale hubs of technology. And when your request arrives, it kicks off a highly coordinated relay race. Tech companies don't just use one giant solitary computer to process everything. They use thousands of servers working simultaneously, in parallel. It goes like this. Server 1 instantly receives your incoming request. Server 2 dives into the databases to fetch your specific video file. Server 3 handles all the security and permission checks. And Server 4 prepares to stream the actual data. This aggressive parallel processing is the exact reason why millions of people can all watch high-def videos at the exact same time without the entire platform just collapsing under the weight. Okay, so once the servers fetch the video you requested, they gotta send that data back to you. But here's the kicker. The return journey is wildly different from the trip there. The data center generates thousands of return packets, but they do not travel back together in a neat, orderly little line. No way. Instead, it's utter, controlled chaos. The network is constantly evaluating congestion in real time. There are a million possible routes home, and your fragmented data packets take full advantage of this asymmetric routing.
To build a truly decentralized and robust system, the internet sends these packets on vastly different global journeys. One single piece of your YouTube video might shoot through a fiber cable in Europe. The very next packet, it might route entirely via Asia just to avoid a traffic bottleneck. Others might hop across completely different internet service provider networks. They are out there navigating through distinct global routes completely independently of one another, just trusting the routing protocols to somehow get them all to the same final destination.
Meanwhile, back at your desk, your computer is waiting. And the timeline of what happens when those scattered packets finally arrive is just blistering. At millisecond 1, packets are streaming in randomly from all those different global paths. By millisecond 2, your computer is aggressively collecting every single one, reading those embedded sequence numbers we talked about earlier to snap them perfectly back into order. And by millisecond 3, boom, the complete web page is fully rendered. All of this fragmentation, global transit, and puzzle piece reassembly happens in way less time than it takes you to blink.
But listen, because the internet relies on these vast physical underwater routes and millions of separate hardware routers, we really have to consider the physical vulnerabilities. I mean, what happens if a massive cargo ship accidentally drops an anchor and severs an ocean cable? Or what if an underwater earthquake strikes? Or a severe storm takes out a major regional data hub? If this were an old-school centralized network, millions of people would lose service instantly. But this system, it was designed from the ground up to be built for absolute survival.
When a physical connection breaks, the system doesn't panic. The millions of routers acting as traffic controllers immediately and automatically update their routing tables to flag the dead zone. Within milliseconds, they dynamically discover alternative paths. All of that heavy global traffic instantly reroutes to bypass the failure. There's no human sitting in a control room urgently flipping a switch. This massive distributed system literally heals itself dynamically through pure mathematics. More often than not, you sitting at home never even noticed that a major piece of global infrastructure just failed.
So the next time you type a web address, or watch a video, or send a quick message, just take a second to remember the monumental physical journey of the data packets making it all possible. Your request was chopped into pieces, routed through local traffic controllers, flashed as laser light through deep ocean cables, processed in massive industrial server farms, scattered across global asymmetric paths, and reassembled right there on your screen in an absolute fraction of a second. The internet isn't magic. It is the largest, most complex physical machine humanity has ever built. So I'll leave you with this. Is billions of machines collaborating flawlessly, healing themselves, and following simple rules at the speed of light actually something greater than magic? I challenge you to look at your devices a little differently the next time you press enter. Thanks for joining me for this explainer, and I'll see you next time.